Okay, let's start. Uh, Sorry, give me a moment. All right, sorry about that. Do you have any questions? Okay. So what we were discussing last time was so chapter 4, right? Markov chain. And 4.1 was basically just introduction, where we were talking about different kind of stochastic processes and what it means to be a Markov chain, right? So let's kind of review the main point. So for a Markov chain, what we need, right, is that we have a stochastic process, right, a family of random variables indexed by time. So indexed by t, right, where t here is discrete. And to be concrete here, right, t will be in the set 0, 1, 2, etc., right? So the natural numbers, I mean, non-negative integers. Moreover, the value, right, of the random variable itself is also discrete. That's what it means to be a Markov chain, okay? So discrete time, discrete space. So most typically, you know, the natural number, the integers is used to describe the state space. Uh, but in like your more typical applications, it'll also be 0, 1, 2, etc. But you can also have negative numbers, right? And so that's not enough, right? Of course, this is just about the discrete nature of Markov chain. What really makes okay, sorry. So one thing that I should say is this, right? The nature of being indexed by time, right, is as followed. And you might recall something like a differential equation where you have an initial position, right? So here, what you will have is an initial distribution, right? Like x0 distribution is given. So maybe let me just say, right? Usually, doesn't have to be 100% of the time, but the way, okay, a Markov chain is given or described is that the initial distribution is given. And it could be just like a constant. So for example, right, in terms of like, let's say weather, right? It can tell you how, right, tomorrow will rain according to, today's weather, etc. But then they'll tell you that today it rains. That means that it tells you initially today, we start at the raining state. Okay. But it can also say that today 50% rains, but 50% doesn't rain. So it'll tell you the initial distribution, okay, of the chain itself. So it's called the initial distribution. And then usually, right, the behavior, okay, so xt is described based on xt minus 1, xt minus 2, etc., x0, right? Doesn't have to be all of this, but it will. So basically, this is just in terms of mathematics, right? We call this a recursion, a recursive description, right? Even though it's more like a stochastic recursive description, it's still recursive description, right? For example, we have seen a lot of this, right? In chapter 3, right? You have two urns, for example, right? You select so many balls from the left urn and you put it in the right urn, and you select so many balls in the right urn, you put it in the left urn, etc., right? And each stage, right, that's what you do. You transfer balls from one urn to the other. So in other words, right, the composition of the urn, the balls in the urn will depend on what you did in the past, right? So of course, right, basically this is a generic description so far, and it touches nothing on the word Markov. But the nature of time is such that you have an initial point where you start, and then you keep kind of flowing right into from past to present to future. So the future is almost always right described in terms of the past, right, leading up to the most recent moment. That's what it means to be indexed by time, right? So far it's just really how things are usually described, but we just listed out here. The reason I say this, right, is because you can think of this, right, the nature of a family indexed by time, by so T, right, is just basically a directed set, right, like I said before, a set with a direction. Well, you could have, right, a random family not indexed by anything, like was or not indexed by time, by a directed set. And the most, let's say the most mundane example of something like that would be, let's say X, Y, and Z, right? This is not indexed by time, right? You see, when you're given X, Y, and Z, for example, well, you just look at three random variables. You can look at their interaction, right? How they interact together, their joint distribution. But there's no sense that, let's say, Z must usually comes after X and Y. There's no sense such as X is given first, then Y is described based on X, and Z is described based on X and Y, things like that, right? I mean, of course, that could happen too. But when you say X, Y, and Z are given, well, they're just given somehow, right? Together. There's no such sense as like progressively, right? Progressively, the story gets told. So that's what it means, right? To have like, let's say, a discrete time stochastic process. Okay. All right. So now to be Markov then, right? The Markov property, there are many ways to say this, right? The sort of like the more formal way to say it is something along the line that the distribution of the next time point, let's say I just want to give it a name here. Okay, I will just call it like this, right? Et plus 1 condition xt in et, xt minus 1 in et minus 1, etc. x0 in e0, okay, must be equal to probability of xt. You know what? Sorry. Let me not be even like this. The reason is, this is fine. Let me just do this. Let me just say E equals to J equals to I. The reason is I'll run out of letters soon, but I'll just say something like I, J, and then let's say this is Descartes I 1, right? And then let's call this, it is called I1, and this is I sub t minus 1, right? And equals to J, xt equals to I, like that. It's only a function of I and J. Okay. So here's the point, right? Again, right? The story, right, is that according to the progression, right? You use the past history, right? This is called the past history. Or if you want, you can also call it the path history. One of course is describing the past nature of thing, but the other one kind of brings up the point that, if you consider, right, where x0 is, x1 is, and x2 is up to xt, you plot them together, you really have a discrete path, right? You have a path of how the stochastic process move in time, right? So, it's really a path, right? So whatever, but basically, right, considering the whole path history, right, and see how the next point in time will be based on the path history, a Markov process or a Markov chain, whatever, or something that has Markov property states that only the most recent history matters, okay? So you can have the whole history, right? Influencing, I guess, how the future is. But then that whole history, what really matters is only the most recent information. And so basically, again, how this will happen is usually coded, right, in the description of how, right, the story progresses. Okay. But the emphasis here is the following, or let's say the challenge, right? The challenge is something that you probably won't realize when you read this description, because it seems very simple so far. But the challenge is exactly when you do this kind of problems, you do the modeling yourself. In other words, you are the one who has to decide what to model. Okay, you have to choose what are you modeling, and you'll see it more as we do more examples today. But basically, the story of a Markov chain, right, in general, or the story of a random variable, right, in this class in general, is that you have to select, or you have to choose what, let's say on chapter 3, what you condition on, right? In the abstract, the formula works, right? Expectation is expectation of conditional expectation. But what is the random variable? What random variable you condition on will decide whether or not your computation will be easy or hard. Same thing here. There are many choices to model, to choose as XT, right? So a typical, the most obvious example here to remember is the example, right, where I say something like, if it rains the two previous day, then it rains tomorrow with probability, let's say 0.5, not rains and rain will rain with probability, let's say 0.8, whatever, right? And two more, right? I don't know, I'm making up number here, but that doesn't matter. Right? So this example right here is, let's say, the first example you see where you have to do some model selection. Because if you let xt be, the random variable that models whether it rains or shine for one day, right? Today only, meaning a two-state Markov chain, right? Then, based on this description, right, which is still, see, this is past into the future, right? The past previous 2 days into the future. If you model, right, if you use xt as the state of only one day, then this will not be able to accommodate this description as a Markov chain. Okay. Reason? Well, because today, right, the most recent information clearly is not enough to decide, right, the future distribution. But on the other hand, with this particular example, right, yes, your choice here will not be a Markov chain, but more or less it's your fault, meaning that you have made a poor choice of modeling, right? So this problem is possible to be made into a Markov chain, and that's the keyword right there. Is it possible to model, to choose something to model, so that the underlying, right, process, the underlying phenomenon is a Markov chain, right? So what to track, if you will, right? That's another way to say it, what to track. What are we tracking as time moves on, right? If you just track today's information, then it will, for this example, for example, it will not be a Markov chain. But if you track, right, the information 2 days in a row, right, 2 consecutive days, which of course will make the states into 4, right? 4 states, then it's a Markov chain. Okay. So that's a challenge. So the question is, when is it impossible, right? To model something, a phenomenon, as a Markov chain, all right? And the story so far may give you the idea or the, impression that, well, it seems like you can model anything as a Markov chain. The answer is no, not true, okay? And again, the sort of the key point is that somehow, if, right, you can encapsulate the information in such a way that when what you choose to model moving to the next point is only a function of INJ, meaning the current state and the future state. It does not depend on the past information, right? By the way, these are just states, I sub 1 sub to I sub t minus 1. These are just notations for states. If they don't in any way, right, depend on the past information beyond the most recent, or, right, also this should be emphasized that they don't depend on the current moment, right? They don't depend on the current moment, meaning they don't depend on what time it is, right? Then it will be a Markov chain. Otherwise, it won't be. All right. So we'll look more into this. And then, of course, right, if possible, then you have to write down, right? Write down the transition matrix. P, okay? So let's see here. I think let's just maybe zone in on these descriptions a little bit, or this challenge a little bit, right? These challenges a little bit. And then we'll look into the Chapman-Kolmogorov equation. So I guess the first question then, right, you were assigned a bunch of problems to work on, right, in your homework regarding this. So the first one is the following. So this is the first question, number 1, right? Here you have 2 urns. So initially 3 whites, 3 blacks. Okay. And then here actually they tell you what to model because they just choose it themselves. They say state, right? I 0, 1, 2, and 3 is the number of white's ball in the first urn. At each step, you draw 1 ball from each urn and transfer, right? And place in the other urn. Okay. And of course, let xt, right, be, so when you describe the state like this, you kind of also, right, say what xt is. Xt is the number of whites, right, in the first urn after t steps, right? So let's pause here a little bit and see, right, that these sort of have all the ingredients that I was telling you about, right? For example, this one right here is the initial distribution, right? Well, of course, we have to see what we're tracking. So we're tracking a number of whites in the first urn. So basically here tells us that x0 is 3, right? So that's the initial distribution. Then they tell us how, right, the system progress. Of course, again, it doesn't have to be something mathematical because, right, things are never that easy. But you're given some sort of like, process, right, on how the states move, the system moves. And basically, but you still see, right, the rough idea of it is you draw 1 ball from each urn and place in the other. So clearly, how the composition of the whites in the first urn will be depends on how the composition of the whites in each urn right now, whatever now is, right? So that's exactly, again, how the future, right, progression depends on the past and the present, right? That's all there is for now. And of course, the question is, right, is XT a Markov chain? If yes, write down the P, right, the transition matrix. So, of course, number one, being the very first question of the chapter, is easy in the sense that they give you, right, what they're tracking. But still, right, I mean, the questions worth thinking about were whether or not, right, this is a Markov chain and why. Okay, is this a Markov chain? So here's something that you see I'll keep saying, right? That basically something is a Markov chain if probability xt plus 1 equals to j given xt equals to I is completely determined. Again, it's really just a phrase, right, that I use when we need to qualify, right? Because what does completely determined means? Completely determined here means that you can write down as a function of I and j, as we said here. But also completely determined means that when you read the problem, you can write down definitely without any question on, well, but I will also need the past information to be able to write, right? You know, this transition probability down. And so here, right, you have to kind of really think about why this statement will imply that xt is a Markov chain. Okay. And of course, again, the word why here would require you to understand what completely determined means. But right, so again, what I'm saying is that we can write down, right, the transition probability without wondering about the past. If we can do that, then that's a Markov chain. If we can't, it's not, right? So let's see. What does 0 move to 0 mean here? 0 means no white ball in the first urn. And then after, right, by the way, so here, the process, right, has two steps. I mean, the process has two transitions, right? You move a ball from the left to the right, and you move a ball from the right to the left, right? So two steps here. So initially, there's no white here, right? So basically, 3 blacks here, right, and 3 whites here. What's the probability that it remains like that after the movement? Well, the answer is 0, right? Why? Because if you have all blacks here, right? And then all whites here. Then, okay, I guess here we have to kind of understand this process, right? As sort of like you simultaneously, right, pick a ball from an urn and put in the other. Because of course, if you transfer a black into here, it's possible, right, that you also select a black back. But the language here is that, well, you simultaneously select a ball from each urn and then swap. And of course, if that's the case, then, right, if you select a ball here, you must select a black. Here, you must select a white. So you cannot, right, this is guaranteed that one white ball, right, will be transferred into a left urn, okay? So in that sense, right, it's kind of clear that this will be the transition probability for the initial stage. Any question about this kind of description? And then, right, for the second row, right, when the state is 1, how does that work? If you initially have 1 white and 2 black here, right, and 2 white and 1 black here, where can you go? Can you go to 0 white? With what kind of probability? Well, the answer is you can, right? If you select a white here and a black here, right, then you can go from 1 to 0. And if you select white here and a black here, then the probability clearly is 1/9, right? You can stay the same, meaning, right, 1 white under how many cases? 2 cases, right? Either you select a black here and a black here, the probability 2/9, or you can select a white here and a white here, with also probability 2/9. This is 4/9. You can increase into 2 whites by selecting a black here and a white here, right? That's the only two. This is the only way. So that's 2/9. Oh, sorry. Hold on. You can increase into 2 whites. Let me see here. Yeah, right. Yeah, by selecting a black here and a white here. So that's 4/9 actually, right? Because it's 2/3, 2/3. And 0, right? Notice, right, that the sum here of the rows so far is equal to 1. Okay. And so, I mean, let's skip the last 2 rows, right? And I'll let you figure that out. But the story is that, right, the way we describe things on how, right, the next composition or the way the you know, the urn, right, the number of white balls in the first urn is composed, clearly only depends on the number of whites before, right? And sort of like when you draw the picture, it's clear because once you know number of whites in the first urn, you automatically figure out the composition, right, of whites and blacks everywhere else, which means you can compute out the probability moving into the next state completely. So that's what I mean by completely determined. So yes, right, this is a Markov chain. And you know, the transition probability is like so. Any question? All right. So let's continue with the second question. The second question will be a bit strange, but this is question number 4, where you're given that P and Q are transition probable matrix. So they say on states 1 to M. So basically they're telling you, right, that these guys are M by M matrices, right? But here, I guess they don't have state 0, whatever, but it's just worth paying attention to. And then you have the process as follow. There are 2 parts. The first, so here they also tell you what they're encoding. So there's a process that starts at 1, and then you flip a coin. With probability of head is equal to little p. Okay. If it's head, so here's the thing, right? You start at state 1 and then you flip a coin. Okay. So if head, then you use P as a transition matrix. If it's tail, well, you guess it, then you use Q as a transition matrix. Then clearly the question is XT a Markov chain? If yes, give its transition matrix. If no, explain why not. All right. So first, right, let's make sure we understand the question. Is the description clear here? So what are we describing, right? And again, right, this is just to give you an idea on how, let's say, rich, right, the description of a Markov chain can be. So basically, I mean, just to make it simple, let's say M equals to 2, right? It can be way more, but so basically, let's say you have, let's say 0.5, 0.5, 0.2, 0.8, that's P. And let's see, Q is 0.4, 0.6, 0.3, 0.7, right? I'm just making things up. All right, so these are 2 transition matrices, right, when M equals to 2. Now, if you say that you start at state 1, so this is 1 and 2, right? That's how they want it, only state 1 and state 2. If you start, right, at state 1, and then let's say use P as transition matrix, meaning you say, well, from 1 I will move to 1 with probably 0.5, from 1 I move to 2 or whatever. Then that's clearly a Markov chain, no doubt. Similarly, right, with Q. But here, to make it more fun, I suppose, right? You start here and then you flip a coin, and then you choose which one you will move, right, with. Is that action still a Markov chain? And why? So again, right, what's sort of like the key question we can ask to help us decide? The key question you can ask is, can you write this down? Probability xt plus 1 equals to j, condition xt equals to I. Are you able to write this down? If you can, most likely it's a Markov chain. If not, no. But you have to explain why. Well, can we? Well, so here, right, what do we need? So what we can do, right, is the further conditioning, right, formula that we talked about before, right, that I told you will be very useful later on. This is back in chapter 1, right? Which says what? Probability of E given F is equal to probability of E given F G times probability of G given F plus probability of E given F G complement given F, right? Remember this? So the point is, right, you're doing conditioning, but you say you feel like you need more information. This formula allows you to further condition, but you will need, right, to pay back by multiply with the probability, right, of that further information based on F. And that, right, sort of like, it's like the law of total probability, but just the conditioning version. So you can also say it that way, right? This is a law of total probability conditional version, right? Anyway, so applying this formula to this situation, what should we condition on further to help us determine this? Well, clearly we want to condition on the result of the coin flip, right? So that's what we need to be able to decide which transition matrix being used. In other words, we will say, right, that this is probability, right, of xt plus 1 equals to j given xt equals to I, and the initial flip is head, correct? Times probability that the flip is head, condition xt equals to I, plus probability of xt plus 1 equals to j given xt equals to I, given the initial flip is tail, times that. And notice, right, that you can almost immediately see that this is the kicker right here that will decide whether or not we can write this down. The reason is, of course, right, what is this? Well, if the initial flip is head, then use P as transition matrix. Then clearly, right, this is just Pij times something plus Qij times something. I put a question mark here because well, it's that. But can we write this down? Do we know what this is? Well, just make it clear, right? The probability of head is P, yes? So is this P and 1 minus P? Just to kind of drive the state home. Because if it is, we're done. If it is, then we're done, right? This is Markov chain. Is that true? The answer is no, it's not true. Because P here would be probability that you get a head. And 1 minus P is probably you get a tail, not the conditional probability that we are requiring right now. And by the way, you cannot cheat and write a formula like this, because that will not be the further conditioning formula. All right. The further conditioning only requires that you write it like this, and that's the correct calculation. So let's try to explain why this may not be P or should not be P. Reason is pretty simple, right? Because this is xt is in state I, and clearly whether xt is in state I or not heavily influenced by whether you use P or Q, right? For example, let's say that state I is impossible to get in. I don't know. I mean, something like this, right? I'm making things up again, but let's say state I is impossible to get in if you land on the Q version. Then if you know you're in state I, then you almost know, right, for sure that you use the P version. That means probability of head equals to 1 rather than P. You understand? Or to make it a little bit more mundane, whether or not you are in state I at time T heavily depends on whether you use P or Q, if the distribution of P and Q are different. So you flip that around. By observing that you're in state I, it should give a different estimate on whether the coin lands head or lands tail initially. All right. In other words, we can't write this down. So this is not a Markov chain. Okay. Or to clarify the matter further, really, right? I mean, the only way we can determine this is by observing the whole past history, if you will. But this we don't need to go into this. But what I'm trying to point out, right, is that by observing state I only, it you know what? Well, let's skip that. What I'm trying to say is this: that basically, by observing, right, xt as state I only, you cannot write out it's purely a function of I and j, how this will be. But you really need to drag in the whole history in order to decide whether or not, okay, the coin initially lands head, lands tail. Why? Because, right, this is the coin was flipped initially. And so how the coins flip will also influence, sorry, this is x0 equals to 1, okay? Will progress into x1, x2, up to xt. Okay, so in order to decide this, we really have to drag in, the past history, and that's why it cannot be a Markov chain in this case. Any question? All right, so B gives you another Markov chain, proposed process. Another process is called Y, starts at 1, but it says that if the current state is I, then you flip a coin. If heads, then you move to J, right, with probability Pij. If tail, then you move to J with probability Qij. Is this a Markov chain, etc.? So do you understand the difference between A and B? The difference, right, is that A is you flip a coin once, and that's it, right? At the initial stage, yeah, right. And then P or Q is decided after that. Part B, every step you flip a coin to decide whether P or Q is used. That's all it's kind of trying to say, right? Does it make any difference? It's why a Markov chain. Well, what's the answer? Again, we need to look at this and decide. Okay. Now, well, how do we write this down based on the present context? Again, right, the coin flip is what we need to further condition on. So let's do that. Sorry. Now, I'm a bit lazy here, all right? Well, let me not be lazy. Actually, the word head here is a little bit ambiguous because here you flip a coin at all steps, right? Versus on the previous problem, you only flip a coin once. So let me state that this is head at the T flip, like that, right? To be clear, because you see, some problem we need to track the time because you can intuitively feel that it may be different if this would be a T plus 1, if you flip the coin next step, whatever. So here, right, this is the coin flip at time T after you have seen that the state is in state I, right? So just to be clear on the order of things, it's a good practice anyway, right? So what do we have? So again, right, these parts are clear. They are Pij and Qij. The question is, do we know this? Do we? Or the most obvious, right, thing we can put in here is P and 1 minus P. Is that true? The answer is yes, right? Why? Because the description here, even though they say if the current state is I'm copying the book's language, it doesn't really matter because you flip the coin anyway, right? Whatever the state is, you flip a coin to decide whether you use Pij or Qij. So therefore, the coin flip here actually is independent of the state of xt at time I, right? So that's why it's just really P hat and P tail. So it's P and minus P. So yes, it's a Markov chain. And that's the transition probability, so transition matrix. We don't need to write down, right? Whatever. This is the transition matrix in the abstract. Any question? Now here's just a easy check. It's not enough. It may not be enough, but it's a reality check for you to see if you write down something correctly. Let's sum whatever we're getting here over J. What are we expecting? We're expecting this to be 1, right? And if somehow we cannot verify it, we show or we see that it's not 1, then we have got something wrong. But if it is 1, then at least in principle, we're not doing something terribly wrong. Okay. But is this 1? Is this equal to 1? Well, the answer is yes, right? Because Pij and Qij are transition matrices themselves. So if you sum over J here, you get 1. Sum over J here, you get 1. So you get really just P plus 1 minus P. So that's really 1. So yeah, at least this expression seems legit, right? And of course, I mean, the argument is wrong, but this is just one way to check. Any question? So there you have it, right? It's really a good example to show you that you could have a small change in the way you describe the progression. And that small change will cascade down, right? The entire history, making the process not Markov. And by the way, right, again, here, they tell you what they're tracking, but you can try to see that in these problems, it doesn't matter what you track, it will still be a Markov chain and not Markov chain correspondingly. You can't really change things by decide to track something else. All right. let's continue with the next one, which is number 8. I think that's a sign, right? Question 8. Okay. So it says that an urn initially contains 1 red and 1 blue. So at each stage, a ball is initially selected. If red, then you replace by red with probably 0.7. If blue, sorry, okay, I mean, red goes to blue with probably 0.3. That's clear. If blue, then goes to blue or red with probably 0.5. All right, is that clear? Okay, so what are we tracking? So the first one is we track the, so here text will call xn, xt, whatever, right? Let xn be 1 if the nth ball selected, meaning, right, of course, this one right here is red, 0 otherwise. Is xn a Markov chain? Again, right, you know the routine, I won't write down. If yes, write down the transition matrix. If no, explain why not. Yes or no? So once again, right, it's really about writing down the transition matrix. And here there are only 2 states. So it's very easy, right? And you can even do a thought experiment where you can do, I'll switch to, by the way, right, the textbook likes to use n for time. I like to use t for time. Technically speaking, n is reserved for discrete notation, t is reserved for continuous notation. Doesn't have to. The reason why I like to use t is because it kind of suggests time, but also because n very often is used for the number of states, right, in the chain. So if you use n here, you have to kind of think about the notation like capital N, whatever, and it might get more confusing, in my opinion. The reasons you see that one of the challenges here is that you will have a lot of notations, right? A lot of symbols to keep track of. So I just want to kind of at least remove one away, right? So I use T for time instead of N like the textbook. Anyway, let's just maybe try out something like this. Can we decide the probability of red moves to red? What does that mean, right? That means that, let's say, as state T, right, state N, whatever, at the 10th step, you know that you select a red. And then in the next state, what's the probability you will also select the red? Do we know the answer here? Well, the answer is we don't. Okay, why? Because when you think of it, well, all right, we know that we select the number, we select a red here, right, at this state. But that doesn't mean that we know what's in the urn, right? Well, I mean, we do know one thing. The urn cannot have two blues, right? Because otherwise you cannot select a red. But it could have been a red, or a red and a blue, right? And you select a red. And you see that clear whether which one it is, right? So you select one red out. I guess another way to say it is what's the remaining color? Because that remaining color will decide the probability of the red selected being selected again, correct? Because if that's red, the probability that, then you will replace blah, blah, right? But if that color, if you don't know it, then you cannot write down the probability, right, of a red being selected at the next state. Or in other words, the composition of the urn at that state really is the point. Or to drive home the point, in some way you can go with the color that you select. So here it's a bit strange, right? Notice this also has to do with what are you tracking, right? That's what I was writing at the beginning. Where was it? What to track, right? What to model. Of course, here the textbook tells you what they're tracking, so you don't have to make that choice. But you have to notice that, right? First of all, in terms of what to track, this is kind of like an odd choice to track. But who knows, right? It's legit. You can decide to track this. The point is, right, that basically, where, how to say this, like whether or not that's sufficient to move to the next state. And the answer is no, because even if you try to track that, is the composition of the urn is what's missing for you to decide, right, the next state. Or if you want to drive the point home, so initially, right, you have one red and one blue. You're given that. So initially you have 50% chance of picking a red ball out of this. So actually, if you decide to do this, then x0, you notice right here, just to also show you, x0 here is 50-50. Right? So in contrast to all the examples we've done before, this is a initial distribution. I mean, a proper distribution rather than, just a fixed state, right? But what I'm trying to say is that if you start out with 50-50 chance of picking a red, and you keep tracking what you picked at each state. For example, you picked a red here, and then you picked a not red, a blue, whatever. Then, right, meaning that you keep the whole chain of what you picked so far. Then it's possible to write down the probability xt plus 1 equals to red. You understand? But basically what I'm trying to tell you is that you have to keep the whole history all the way to the beginning of the color of the ball you select in order to write down the next distribution. So this is a sign that if you choose to track this, the color of the ball, then there's no way it can be Markov chain. And I'm referring right to the trick, and there's a name for this trick. The trick of this. This is called the enlarging the state. Enlarging the state space trick. Right? Because basically, in a way, you don't have to track just a single state. You can track a vector, meaning you can track 2 days at a time, things like that, right? But there's a limitation to this trick. In other words, if somehow the history dependence goes back to all the way to the beginning, like this urn right here, then there's no way you can rename or enlarge a state and still make it into a Markov chain, okay? You have to really change your point of view and decide to track something else, maybe. But as the object of tracking, the color of the ball will not be a Markov chain. The color of the ball selected. Any question? Okay. So B, let Yn be the number of red balls in the urn immediately before the nth ball is selected. All right, and this exactly refers to the composition in the urn that I was talking about, right? Is Yn a Markov chain? And again, right, with the whole blah blah blah. If yes, write down. If no, why not? Yes or no? Well, the answer is yes, right? Because, well, so first of all, right, how many states is Yn in? So Yn here, right, is in 3 states, right? 0, 1, or 2. Okay. And you can see, well, concretely, if we can write down the probability that Y is in the some states, let's say state 2, given how it was before. For example, if there were no red balls before the pick, can you end up with 2 red balls in the next pick? The answer is no, right? Impossible. How about if you have 1 red ball? So I guess right here, I'm attempting to write down the transition matrix for row 2, right? Sorry, for row 0. So 0 go to 0. Can 0? I'm writing down column 2 actually, right? That's fine. Can 1 moves to 2? Or rather, right? I think this is a bad question. In terms of just, row and column, I should do this, right? Can 0 goes to 1? If you have no red ball, can you move to 1 red ball? Well, the answer is yes, right? How? If you have 2 blues, then you are guaranteed to stack a blue, right? So blue goes to red with probability 0.5. And of course, right, blue remains blue with probably 0.5. Like that. And so on and so forth. So yes, this is a Markov chain. Any question? I mean, of course, you have to feel out these things, but right. So right here again, this demonstrates, right, that what to track, right, matters. If you choose the wrong thing to track, then the same phenomenon, right, will not be a Markov chain. The same sort of like whatever you describe, the same experiment. But if you choose the right thing to track, it will be in many ways. All right. So these are on your homework questions. But let's take a look at another one where here, this is just an demonstration of how to model a Markov chain, let's say, intelligently. And here's the thing that you should be used to, right? Let's say you decide the number of flips, right? You flip a coin with probability heads equals to P, right? Until, let's say, the first 3 consecutive heads. Okay. And let n be, right, the number of flips necessary, right? So we've done this question, right, in the previous section. Can someone remind me what is the expectation of n? What's the expectation of number of flips until we get 3 consecutive heads? The answer is 1 over p, 1 over p squared, 1 over p cubed, right? And this is done by conditioning. condition on the number of times it takes to, number of flips it takes to get to 2 consecutive heads. Now, believe it or not, that's still an easy question. Here's a harder question for you. What's probability that n equals to 8? What does it take, right, to get the 3 consecutive heads at exactly the 8th flip? Now, if you think that this is an easy question, think again, right? Because I mean, obviously I can change to 100, whatever, but I won't. Let's just stay with 8. Why would this not be an easy question? The reason is, right, yes, at the 8th step, you get 3 consecutive heads. So you sort of know, right, the 6th, right, 7th, and the 8th are like this, correct? And even grant you that, right, the previous one, the 5th, cannot be a head, because otherwise you get 3 consecutive heads much sooner than that. I mean, not much sooner, but sooner. But what are the compositions of the first 4? And this is probably why I want to change this to maybe not an 8, but maybe a 10, whatever, right? Doesn't matter. The reason is this, right? You have to, if you want to look at cases, and that's not a wise thing to do, but suppose you want to look at cases, then you have to list out all the cases of the first 4 that does not contain 3 consecutive heads. And that's a pain, right? Because you have to list out head, tail, heads, whatever, that somehow does not have 3 consecutive heads in there. All right. And to make it more fun, you can do something like probably n less than or equal to 15. All right, again, I'm just throwing some arbitrary numbers here, but as you can see, that basically the point is listing cases here is hopeless. But right, what we're after is the distribution of n is the question, right? What is the distribution of the number of flips, okay, until the first 3 consecutive heads? And as I mentioned before, right, these chapter 3 are sort of deeply connected to stochastic process, we just don't mention it so. And the reason is some aspects of chapter 3 question, the same experiment, can be done, let's say, simply by conditioning. But some other aspects like this, the distribution question, should be done under a more sophisticated tool, which is Markov chain modeling, okay? In other words, there is a Markov chain here we can track. And by understanding that Markov chain, we can decide the probability of n equals to 8 by saying that this is equal to probability that xt equals to something. And I think here I should have tell you about the Chapman-Kolmogorov equation, because the point is the probability that xt equals to something, let's say 3. This is easy via, right, the Chapman-Kolmogorov equation. Right. So maybe let's continue with this discussion, because, you know, this is about Markov chain modeling, right, rather than the equation. But in case I think some of you have seen this before, but basically this is just p to a tth power, the transition matrix. And then you select like the initial state that you're in, and then, right, the last state that you're gonna be, right, the state you're gonna arrive at. So this is the entry 0, 3, right, of the matrix, transition matrix P to a T. So the point is that once you have a Markov chain, then to track where it will be given the initial distribution is very easy. Just raise the matrix to a power, right? So we'll get there, right? Via Chapman-Komorov. But so I'm jumping a little bit ahead of myself, but I'm just telling you that it's easy to do. The harder question is to decide what to track. Okay. And in the experiment where we want to track the number of flips until the first 3 heads, what are we tracking? So the most obvious answer here is you just track, let's say, the result of the most recent 3 consecutive flips. What does that mean? For example, right, X5 will track, right? So you don't care what this is, but you will track the result of the most recent 3 flips. In other words, the 3rd and the 4th and the 5th flip. You will track the result of those. Okay. So, oh, by the way, now that I think about it, this is actually not easy. It'll require something else. We'll explain. So, but anyway, right? I'm trying to demonstrate that. Well, so it's not easy because you have to really describe something else. But for now, right? What I'm trying to say is like at least we're heading toward the right track. Because, for example, right, if you know that these guys are head, tail, head, let's say, then in some way you know that probably you're not getting 3 consecutive heads at the 5th flip. The reason why this is not quite true is because you could have got the 2 heads here, right? So we need to kind of explain that. But the point, right, is that if you track the states of the most recent 3 consecutive flips, then it seems like the right move to go. But is this, first of all, is this a Markov chain? And second, right, what's the cost? In other words, what's the transition matrix? So is it clear so far what Markov chain we're trying to describe? Or what process we're trying to describe? Okay, now, right? What's the cost? So first of all, it should be easy to see that if you track the states of the most recent 3 consecutive flips, then you can, right, drive transition from one state to another, right? You can write that down. But how many states are we talking about? How many states are we talking about? The answer is 8 states, right? Because you track all possibilities of the 3 most consecutive flips. All right? And that might seem fine. But first of all, notice that you have an 8 by 8 transition matrix, which may not be fun to raise it to 10th power, whatever. Okay. But well, you think you have a calculator, so you can do it fine. But you will see that very soon this is not feasible because 3 consecutive heads is just really 3, it's just a number we throw around, right? What if I want to track the number of flips until the first 10 consecutive heads? Then if you track the number of flips, the states of the most recent 10 consecutive flips, you get 2 to the 10th, which is what? I don't know, 1024, right? I'm not sure if that's a number, but whatever, right? You get about 1,000 states, meaning you get 1,000 by 1,000. I mean, whatever, right? Matrix, which is huge to think about. And is it even wise? Is this really what we need to track to get to so many consecutive flips? The answer is not necessary, right? You could be very economical with what you try to track. So you could do this. You can track the number of consecutive heads up to whatever you need. In the most recent clips. In other words, right, here xt will be 0, 1, 2, 3 in our discussion. How so? So what I mean, right, is that if you so far has only one head, right, at the T flips, right, after T flips, then, right, this is 1. Of course, right, if after so many flips you get a tail, then it's 0, right, even if this is a head. We understand? This is state 0. A tail head will be state 1. Head will be state 2. Head will be state 3. All right. So we track the progression of the number of consecutive heads. And you see that, right? This is like in terms of CS language, right? This is a linear growth rather than exponential growth in terms of the complexity of, let's say our algorithm, right? And whenever you have a linear growth, it's a much preferred, right, approach. So let's demonstrate, for example, right, that, well, of course, the question remains that when you try to be economical like this, is this still a Markov chain? For example, right, how can you go from state 0 to state 1? Or state 0 to state 0? If you have no consecutive heads, right, how can you get to one consecutive head? I guess the word consecutive here doesn't mean anything, right? But it will be P and 1 minus P, right? Because if you're at a tail, then you get to a head, right? From P, and you get 1. How about 1 moves to 0, 2, 3, and 1? If you're at state 1, right? Meaning you get 1 head so far, and then there's a tail here. Then I guess the only thing you can move to, right, is either 2 heads or no head at all, right? You cannot stay at 1 head. So therefore, you get a P 0, 1 minus P. If you get 2 heads so far, you can move to 3 heads, or again, the pattern is spoiled. You get no heads, right? Because if you get a tail here, then you get no, it's the most recent, right? Flips, so you get no head. So again, right? P0, 1 minus P0. What about 3 heads? Well, in this particular problem, at 3 heads, you're there, meaning that you get what you want. So you want to make 3 into an absorbing state. So you don't want to move anywhere from there. So 3 absorbing. We'll explain more about this later. Okay. But this example demonstrates yet another aspect of Markov chain. And this aspect is not really about being Markov or not, but it's about being economical with what to track, the complexity of the algorithm, right?
Professor,
In the previous, yeah.
all right, first for the wouldn't every single state go back to state 0 if you get a tails? Because you have one.
No, thanks for correction. You mean here, right? Yeah, no. I wrote it wrong. Yeah, appreciate it. Yeah. The last one is 1 minus P is 0. Yeah, thanks. I wrote it wrong.
Okay,
Yeah.
and it doesn't
Mm.
factor in for the third state because we're just done with the question.
Yeah, right. It wouldn't not done, as you'll see, right? We'll use this to do the calculation, as in the Chapman-Komorov equation. And I haven't told you, right, this, and it's a little bit more sophisticated because really the question is not about you and you land at state at 10th step, because the point is that you could have been at state 3 in the previous steps, right? It has to do with the word the first time. So we have to talk about absorbing state and things like that. But yeah, so basically, yes, the partial answer is because once you're there, you don't want to move away from anywhere else, right? That's your goal. But also it has to do with the Chapman-Komorov calculation, and you'll see. Yeah, but yeah, partially correct. Yeah. Okay. Any other question? So, right. So, as I was explaining, right, the point of this question, this example, is to show you that, right, there are many aspects of Markov modeling, and sometimes efficiency or complexity is the point, even, right? As in here, you see both ways of modeling give you a Markov chain. So it's not even a question of being Markov or not, but it's a question of about complexity. While some other examples show you that if you choose the wrong thing to track, it will not be a Markov chain. Okay. All right. So now we're done with the modeling aspect. Okay. Like what to track. I mean, by that I mean I think I've shown you enough examples, right? But of course, the rest is up to you to implement. And now we'll move on to the Chapman-Komorov equation, which is 4.2, I think. All right, so so here, this is exactly, so let me say this, right? At least the use, and then the use here will be more complex than description I'm gonna write down, but at least the use is to calculate, let's say, future path, okay? Probabilities given the current state. Let's say current information. All right, so Let's see what is. Now, the context is that we have a Markov chain with transition probability, with transition matrix. P, okay? So, first of all, what this means is that we know this. Okay? For all T, I, and J. We know this, right? But of course, right, the natural question is, what about 2? So this is, you can call it one step, right? One step transition probability. What about 2-step transition probability, right? And well, what's the answer? The answer is, of course, via the law of total probabilities, right? That further conditioning that we talked about before. Let's say by further, right, conditioning. What are we conditioning on? Well, clearly we're conditioning on xt plus 1, right? Why? Because the transition matrix is it's not the only thing we know, but it's what we must rely on. And transition matrix, by definition, right, is a one-step, right, one-step transition probability. So if we further condition, you get that, right? This probability will be, right, the probability xt plus 2 equals j, given xt equals to I, and let's say xt plus 1 equals to k, times, right, I have to write down a second line here because I'm out of space. Like that, right? But here, right, notice before we have something like G and G complement, right? Because there we just look at the world as 2 parts, either G or not G. But here we're listing the state space. So we need to sum over all possibility of K, right? Here we sum over all possibility of K in the state space. Okay, like that. So this is the law of total probability again, right? Conditional version, or you can call it further conditioning, whatever you want to call it. Okay, so far. But then, right, notice that Markov property kicks in here, right? Because here you have xt plus 1 and xt information, and being Markov, right, only the most recent information matters. So you can drop, right? And then, of course, this is pik, that's this one, times pkj. All right. Any question? But so you see it, right? What is this? Well, this is row I, right? Because you're fixing I, you runs K over. So you sum a row of P, row I of P times a column, right? Column J of P. And that's an inner product, ith row, J column. And if you recall, right, matrix multiplication, the ith J entry of the product is the ith row times the J column. So this is really P squared IJ. Okay. Any questions so far? So you can consider this as an induction step, right? That's a first induction step. So what's the induction step? What about we want, let's say, m steps ahead or n steps ahead, whatever, right? And this is why you want to use t as time, right? I want to do n step, right? Transition probabilities. Well, again, right? I would, so I move here, right? Condition on what? It's up to you. You can either condition on xt plus 1 or xt plus n minus 1. Doesn't matter. Let's condition xt plus n minus 1. So you understand what's going on here, right? I condition on the immediate step before t plus n, right? T plus n minus 1. And I sum over all possible states that it can be. And so you see, right? First of all, using Markov property, I can drop this. All right, that's clear. And second of all, right, this guy is just a one-step transition probability, right? So that's PKJ. The induction hypothesis, so the right, allows me to suppose that whatever I was proving so far holds for the -1 case, which means it's a power, right, to the n minus 1. But you see, right, same story goes, ith row, but now of the p to n minus 1 power, right, matrix. So anyway, this is p to n. So that's Chapman-Kolmogorov for you at the most basic level, right? The nth step transition probability is the nth power matrix. Read off the entries. Any question? Okay. So let me just say one more thing. So, like I said, sometimes you have something like an initial distribution. All right, and here the distribution is denoted by pi. All right, what is pi? Pi is a vector of size 1 by what do we call the number of states here? I don't know. Let's say n. But this is n is number of states. Okay. So what do I mean by this, right? So I is a vector that's sum to 1, right? So it's a vector of probabilities, right? Like 0.1, 0.2, 0.4, whatever, right? So if we have 3 states, then this is an example. So it just basically tells you that the probability that x0 is in state 0 is 0.1, state 1 is 0.2, state 2 is 0.4. Okay. But if you have an initial distribution, then what's probability? Let's say xn equals to, I don't know, j. So notice this is an unconditional probability. Right? Unconditional. Because you're not saying condition on x0 equals to something. But it's easy, right? Because we just have to do the law of total probability conditioning on x0. And now you sum over all possible i's. But you see, right? So I guess what I mean here is, right, probably x0 equals to I is what I call pi. You know what? Let me do a superscript here, right? Because subscript is already for the state. Yes, and then p to the nij. But you see, right? This is you sum over all entries of pi times the jth column, right? This is the jth column of p to n matrix. So all in all, you're just really doing the inner product of this is a row times a matrix, right? A row times a matrix is a row. All right. And then you read off the jth entry of that vector because row times a matrix gives you a row. So 1 by n, this is n by n. Are we clear on this? And this also covers the case, right? When you start out with a fixed state, you can say, well, what if I start out at state 2? I know that. Well, then you can still have initial distribution, but it will be something like 0, 0, 1. So this covers, right? The concept of initial distribution covers even this case when you do this. Doesn't matter. I mean, if you have this, then you can use this as the quote unquote initial distribution, or you can just do, P to Nij, the old-fashioned version. But I just want to say that, right? If you have initial distribution, then it's left row vector times the transition matrix to so many powers, and then you get it. All right, any question? So far, right, we've been just talking about a point, really, right? This is n-step transition probabilities, but it's a point. So by a point, I mean one point in time to 1 point in time. But literally, right, it's a Kolmogorov, Chapman-Kolmogorov can be used to calculate the whole path. What do I mean by path? Here's a path for you. And here, let's say xn is equal to I sub n. Xn minus 1 is equal to In minus 1, etc. X1 equals to I1, X0 equals to I sub 0. All right. So this is the path, right? And what's the difference between this and this? Well, the difference is clear, right? Basically, you're given the current state, whatever that is, and you look at n steps into a future where you dictate where they are at each point. Is that okay? So this is a path. Okay. Can we write this down? Well, the answer is yes, right? If you recall yet another law that we wrote in chapter 1. So first of all, right, by definition, this is just probability xn equals to I sub n, xn minus 1 equals to In minus 1, etc., right? X1 equals to I1, x0 equals to I0, divided by probability x0 equals to I0. Okay, that's just definition. Now we'll work on the top. How? Remember, right, if you have an intersection of so many events, you can do a cascading, right, conditioning. so on and so forth, right? I won't write more, but you know what I'm saying. Basically, you condition here on all the previous steps, and then you take that most recent ones, condition on all previous steps, etc. Right? The last one you end up with is probability x0 equal to I0. And then you divide, right, by probability x0 equals to I0. Okay. And then, right, you use Markov, right? You use Markov to drop all the dependents except for the most recent one. So in other words, right, what you have is something like this, right? You have P, but in minus 1 to in. That's this guy. And then here you have P, but in minus 2 to in minus 1. All the way down to P I0 to I1. Like that. Is that okay? So basically, it's really a chain, right? But it's not anything like a power of P, right? Because it's really a chain of probabilities where you move from one state to the next with that kind of probability. Right. So for example, if you have state 1, state 2, state 3, right? I know 0 0.1, 0 0.4, 0 0.6. Let's say, I don't know, 0 0.5, 0 0.5, 0 0.9, whatever, right? Just something. Then suppose you have a path 1, 2, 3, 2, 3, 2, 3, whatever. Then you just do something like 0 0.1, 1 to 2, 2 to 3, 0 0.4, 3 to 2 is 0 0.5, all the way up, right, to 2 to 3, 0 0.5. It's the most natural thing that people would do, right? But just don't forget that what really works behind the scene, right, is this cascading probabilities conditioning, and then a Markov property, right, that allows you to do, let's say, the most natural thing in the world, but there's some mathematical reason behind it. Any question? All right, so if not, I think it's a good place to stop here. We'll continue, okay, on Wednesday.